All right, so a lot of times the sound takes about 10 seconds to kind of kick in on this app that I'm using to make these videos, but so we should be probably pretty good right now. Hi guys, welcome to Online School Week and welcome to some strange times, but nonetheless, like I said before when you guys heard me in class, the honors chemistry train will still keep moving along. So a couple things to remind you of, and again, make sure you guys follow at Whiteboard Mr. P on Twitter. I'm going to use that as a way to be able to kind of send links, remind of things, and everything will be mirrored and sent in emails as well too. You guys can kind of see what we're doing for the week. You'll be emailed this file ultimately. But before we start, my teaching assistant, Anders, here has a couple of words to say.
Hi guys,
Talk loud, buddy.
Hi guys, I've been doing these emojis. I've been doing how to draws. I've also made a dragon in 2019. It's just kind of flashback from when I've done it. But here, one emoji. I've done most of these with my dad too, but like this one, this one, and then this one, this one, this one, and this one I did all by myself, starting from the barfing rainbow one.
I'd say this one's probably the fitting one, the crazy face, right? Okay. What else do you got to say to these guys? Come back here to the camera.
Now you have to listen to my dad. Bye.
All right, so thanks, Anders. Hopefully, you know, eventually at some point we'll be out of my kitchen and I won't be in my baseball cap, and maybe we can have my teaching assistant make an appearance in the actual room at some point. So, anyway, so today what we're gonna be doing, we're gonna be, and I'll eventually send you the link to this video, obviously, but and you'll get this all updated when I kind of do the final plan for the week. But we're gonna go over the solutions from before break with the Lewis structures, and we're talking about how to do Lewis structures for ionically bonded substances. And then I'll assign the worksheet today. It's in the lecture. You'll pause the video, write down the questions, and then you guys will work your solutions. And that is due on Wednesday. And then Tuesday is we're going to check in on the forum, ask any questions you guys would have. I got another short lecture that I'll send you the link for, and then you guys will, after check-in, continue your work. And that's kind of it for today as far as reminders. You know, just a couple of things as I'm getting the screen up. Just make sure you get, you know, hey, you know what, this is maybe a little weird, a little strange, but we'll get through it. You guys will do fine. Have some fun with it. You know, I welcome you when we're in the forum to, you know, share some comments. What are you doing? Make some jokes, that kind of thing. I got a pretty dry sense of humor, so I'll probably crack some funny things too, or at least try to. You guys will all do the old Mr. P, whatever. I know I'm a big, incredible science nerd. So here we go. Here's the Lewis structures you guys worked on for homework. The three, and let's talk about kind of the solutions for this. So if you remember, I had kind of commented a little bit. I'd kind of made a bit of a mistake, and I kind of assigned this one in my mind thinking it was resonance, but the more I thought about it, the more I realized that it was actually showing isomerism. Remember, the difference between resonance and isomerism is that can kind of go back. You know, resonance, there's two or more sort of possible or plausible ways, right? The same orientation though, right? So we looked at some of the examples. We talked about, you know, resonance doesn't change sort of the orientation. It's more about where you have the location of maybe the single or double bond. Whereas isomerism, right? But for example, the difference is that isomerism, there's the same formula, but really a completely different shape, okay? Or different structural alignment, however you want to say it. So this would be probably, I would say that this one falls more into the category of isomerism, right? So you got the two carbons, central carbons, singly bonded. and then single bonds to the chlorides and the hydrogen. Chloride abides by an octet, so, and hydrogen abides by a duet, so which we've talked about. I just realized I might have made a mistake here. No, it's easy. I can correct this one. Anders just got angry at me because I had realized I had made a mistake a couple minutes ago. All right, here we go. Mistake is corrected. Okay. Double bonds between the carbons. So Anders, I corrected it on the fly. So here we go. The 8 carbons are on, 8 electrons are on the carbon, 4 bonds total. Carbon has 4 valence electrons, wants to make a total of 4 bonds. So double carbon to carbon bond. And then single bond to the chloride. And probably the biggest mistake that I saw with what you guys handed in when you handed these in, you guys did a really nice job, but is you forgot to put the unpaired electrons that were owned exclusively by the different atoms. Okay. Again, why do I call this, isomerism, right? Is because in a sense, you have, let's say this is carbon atom number 1 and this is carbon atom number 2. Well, in this case, I put the hydrogen on this carbon atom number 1. In this case, I put the hydrogen atom on this carbon number 2. Okay. So I would lean on calling this isomerism. This one's a little bit confusing after I thought about it, and that's why I sort of said to you guys, don't worry about it so much. Like I wouldn't necessarily ask you one, maybe I like this on a quiz, just because it is a little bit of that gray area. But the structural piece of doing the Lewis structure itself was sort of the key part to this. The second one, CF4, again, single carbon to fluorine bonds. Fluorine is, I got a couple of missing dots there, huh? Okay. Fluorine is 7 valence electrons. It's in group 17. It wants to have 8. So it's going to have this tendency to form a single bond. Carbon has 4 valence electrons. It wants to form 4 bonds. And then we have these single carbon bonds to each one of the fluorines. Remember, the first atom listed is usually the central atom. So we see a distribution where the carbon is central and then the fluorines are on the outside. Again, probably the biggest error that I saw looking back at your work was you guys forgot to put the unpaired electrons on the Lewis structure. We do want to include those, okay? And then the last one, the HOCl. This one's kind of an interesting one, and part of the reason why I picked it was because of it brings up a little bit about, we'll get later on this week talking about sort of bond shape of molecules, right? And in the Lewis structure for an individual atom that we talked about, oxygen usually has the unpaired electrons that it's going to want to give up, or not give up, but share its bonds sort of on these opposite corners. Okay. And there's a reason why that is. Molecules will form certain shapes. These 3-dimensional shapes help determine things about their properties. And we'll get more into that kind of later this week and have some discussion about that. And again, I wouldn't have, taken anything off, but the oxygen in this case is the central atom. It's not always the first atom that's listed as going to be the central atom. That's part of the reason why I picked this. But that oxygen has 6 valence electrons. It has a tendency to want to create 2 bonds to get to 8 valence electrons. And there is a reasoning behind why I put them on angles here, as the oxygen formed its single bond to the hydrogen to get hydrogen's duet, and its single bond to the chlorine to get chlorine's octet. Okay. And it's because of in nature, the way that the atoms are distributed around a single unpaired electron or unbonded electron of oxygen is that these bonds are going to have a tendency to form on angles. Okay. And again, we'll talk more about that later this week. All right. So enough of that on the solutions. Hopefully this helped a little bit in kind of clarifying what you guys did. Whatever that was last week, I guess. I'm losing track of time, but when I did that homework. Okay. All right. So now moving on, we're going to talk Lewis structures for ionic bonded substances, and this is a little different than with the covalently bonded substances that we've been working on. So when we're doing Lewis structures for ionic bonded substances, it is a little bit different. So remember some things, and because one of the things when you guys get to ultimately the quiz is that you're not going to know, is this a covalently bonded substance? Do I use dashes? Okay. Or is it an ionically bonded substance? So do I need to use this sort of new technique that we're going to teach you right now? Well, the reality of it is, remember, typically it's to look for that metal and non-metal together, right? If it's a formula that has a metal and non-metal together, that's an indicator that it's a ionic substance, right? Or an ionic compound. And if it's an ionic compound, right, that means we're going to use sort of this special technique that I'm going to talk to you about in just a second on the pages to come, and including the fact that we're going to use some color coding, at least initially in this, to help you guys understand how electrons are owned. Because in ionically bonded substances, there are no sharing of electrons. So we don't use dashes. One thing that is going to be helpful that you're going to want to pull out or find in your stuff or materials is a common ion sheet. That'll be helpful in writing and drawing these. All right, so let's talk about some examples to kind of talk you through this. Okay. All right, so next slide. Oops, how'd this get in here? No. Yeah, Brecken, my daughter, she made some artwork here. I don't exactly know what this is, but I thought it was pretty cool.
Kind of looks like a queen in a castle.
A queen in the castle. There we go. I think maybe that's what it is. Thanks, Anders. All right, so there's a piece of Brecken's artwork to break up the monotony today. Here we go. Drawing ionic Lewis structures for ionic compounds. So, hey, here we go. Let's use NaCl, sodium chloride, as our first example. So individually as Lewis dot diagrams, sodium is in group 1. It's got 1 valence electron. Chlorine is in group 17. It's got 7 valence electrons. Okay. We know that it's a metal and a non-metal, so we know that it's an ionic compound. We know that in ionic compounds, what happens? Electrons are going to be not shared, but completely stripped or lost and obtained. So the chloride it's one electron short to get an octet. It's going to rip that electron away. Sodium, it's kind of like it's got this extra electron just hanging out, so it just wants to get rid of it. Right? This is something that we've talked about as far as location of the periodic table, all that good stuff. Okay. So sodium chloride, the electron places itself within the valence shell of chloride, and now chlorine becomes chloride by taking ownership of that electron. So when we draw this, what we want to do is we want to show electron ownership. So the chlorine has now gained that electron, and I'm color coding it in red to show that originally this electron here was owned by sodium. But now, because chloride has taken it in forming this ionic bond, it's now in the circle. The circle is showing or representing or showing electron ownership. Because of that electron ownership, because chlorine has obtained that electron, it now has a -1 charge, right? Because sodium has lost that electron, it's obtained a +1 charge, okay? So this is how I want you guys to draw these for ionically bonded compounds, so the Lewis structures for ionically bonded compounds, to show original ownership electrons using the color code, and then the circles are going to show electron ownership, and then you're going to write in the charges. So here's another example, okay? Magnesium chloride. So magnesium is, it's a metal. Chloride or chlorine is a non-metal. Magnesium, typically it's in group 2, so it's got a +2 charge. Chloride is in group 17, it's got a -1 charge. How do we show that? Okay, so again, I used red to represent the magnesium. Okay, it originally owned these 2 red electrons. Okay, chlorine in green had 7 valence electrons, represented in green. And now as it forms magnesium chloride, the chlorine is going to overtake or now completely possess the electrons from the magnesium. Now, when that happens, right, the charge by each chlorine is going to be obtained as -1. Okay? Because magnesium lost 2 electrons, its charge now is +2. So again, this is what I would want you guys to draw. Okay? And you're going to show that charge for the individual ions. Okay. Now, one thing I want you to kind of notice, why is it that, why do I have the magnesium sort of written like this, and why don't I have the sort of the chloride here and maybe here? Okay. Or because here's the deal, right? It kind of goes back to when I taught you guys about where do we place the individual electrons around the Lewis dot diagram for an individual atom. Well, magnesium's in group 2 when we showed you this. This is out of the textbook, right? Magnesium has 2 valence electrons. We always distribute them sort of side by side on opposite sides of one another. So therefore, when the chloride joins the party and strips those electrons, the chlorides are going to be to each side, right? What I'm kind of getting at is this. When you write these, you don't want to do it like it's not magnesium and then chloride and then chloride. Okay, that's wrong. All right, one more example, and then we'll kind of get you going. Okay, so calcium oxide, again, metal, non-metal, right? Calcium is in group 2. So it will typically have a +2 charge. Oxygen is in group 16. It's got wants to typically have a -2 charge. Oxygen is 2 electrons short, okay? And therefore it's going to obtain a -2 charge. Calcium has 2 electrons to give up. It'll give up those 2 electrons to the oxygen to become oxide. Now you do need to notice a little bit, right? Again, this goes back to what we kind of talked about a few minutes ago. The Lewis dot diagram for an individual atom of oxygen is this, right? So when we place the 2 electrons that the calcium is giving up to it, we can't place them in the same side, because remember, the side represents an orbital. Each side represents an orbital. Each orbital can contain a maximum of 2 electrons. So this would be wrong. No, so I got no written here, right? Okay. This is incorrect because when electrons are gained by the oxygen to become oxide with a -2 charge, it's going to obtain those 2 new electrons in those 2 orbitals that are opposite of one another, okay? Because it has 2 half-filled orbitals to begin with, you're filling up those 2 half-filled orbitals with the electrons that calcium's willing to give up. So not this, this is wrong, right? Because of the Lewis dot diagram of oxygen as an individual atom. Okay, and that's that one chart earlier in chapter 7 that we talked about. This does come into play a little bit about shape, and again, we'll have some more discussion about shape down the road. Anyway, bottom line is this. Here is what you would draw for the Lewis dot diagram or Lewis dot structure for calcium oxide. Again, remember, it's an ionically bonded substance, metal, non-metal. So therefore, you don't use dashes. No dashes are used. Okay. All right, so I suggest, like, anytime, and I should have said this right away, but anytime you guys ever, if you gotta go back, you can rewind, you can pause, take notes. You can go back and review this all you want, no big deal. But here is the worksheet that is ultimately due on Wednesday. So I'm going to go to the first slide. Okay, so for Wednesday, the Lewis worksheet, construct Lewis structures for the following covalently bonded substances. So this is where you're using dashes. You're showing covalent bonds. You're showing electrons being shared. You're going to use, show all your dots of the unpaired electrons, like we talked about, correcting the mistakes that you guys made. And there's Anders back there that you guys made on the previous solutions that we worked on. Oh my gosh, there's a ghost. Okay. So pause the video, write these 8 down. Okay. Then here are the second half of the worksheet, and here you go. So you're going to construct Lewis structures for the following ionic bonded substances or ionically bonded substances. So I do want you to color code it. I want you to circle electron ownership. indicate charges. Remember, no dashes are used. The common ion sheet would be helpful here. Okay, so again, you know, we want things to look, you know, something like this, right, where it's color coded. Circle the electrons that are now owned by the negative ions. Okay, so you can pause the video right here. Write down these 8. Okay. So there's the first 8. There's the second 8. And my suggestion to you is to just write these down, show the work in your notes, right? Keep it small, keep it condensed. So you're not sending me 16 pictures. Hopefully you can send this to me in like 2 pictures, right? And then on Wednesday during class time or at class time, I will need you to submit your work on the Lewis structure worksheet, which this is, these 16 Lewis structures. Hopefully that makes sense. And again, I'll see you guys tomorrow in the forum. And if you got questions about what do you mean by this, Mr. P, we can ask those questions tomorrow. And I need a little note here, you know, we will color code on the quiz with Ionic as well. So on the quiz on Friday, make sure that you guys have available, you know, like a couple colored pencils or maybe a marker or something like that. So when you guys are given the quiz, and I'll email that to you, and you guys work on it during the class hour, have those available so you're not chasing those around. And then you'll take a picture of your quiz, and then you'll send that back to me by the end of the hour. Okay. I think that's it for now, guys. We'll see you tomorrow in the forum. And thanks for listening. And good luck. We'll get through this. It's going to be fun. I think I'm choosing to be positive about it, and just keep the old train of trucking and moving forward. And we'll do fine, and we'll get you through it, guys. And apparently the emojis have made their appearance. All right, Andrew, say goodbye.
Ooh.
Say goodbye.
Bye.
Get your face in.
Bye.
All right. See you guys.
See you, man.